everyone. Good morning, afternoon, or evening. My name is Charlie, and I'm an assistant professor at the University of South Florida. Very pleased to host this traffic flow uh, theory and characteristics webinar. I know some of you might come from a late night, so I very much appreciate your attendance. Thank you so much. I also want to thank Dr. Jack Haddad from Institute of Israel and Dr. Jorge Lava from Georgia Tech for the support to this webinar series. And also I'd like to acknowledge my graduate students, most in Pacified's help with technical issues. And before I have the seminar started, I would humbly ask you to mute your speaker, actually mute your microphone or audio unless you want to speak out. So the way to do that is actually simply go to the ribbon or somewhere on top of your, go to webinar control panel, and then there is microphone sign, and if you click it, you can toggle on and off your audio. So that'll help minimize the background noise. And we're going to have a presentation about 40 to 50 minutes, and you'll have some time for questions and answers at the end. I'm going to talk about it later after the presentation. And we're going to record the whole process for information. Now I'm clicking the starting button. Okay, so today we're very pleased to have Dr. Monica Menendez as our honor speaker, and she's the director of the research group Traffic Engineering with the Institute of Transportation Planning and Systems at ETS Zurich. Since the year of 2010. Prior to that, she was a management consultant at Bain and Company. She joined Bain after receiving a PhD and a Master of Science in Civil and Environmental Engineering from UC Berkeley in 2006. During her studies, there she received, among other awards, an NSF Fellowship, the Gordon Newell Award, and the Outstanding Graduate Student Instructor Award. In total, she is the recipient of more than 20 scholarships and awards from well-known and prestigious organizations, professional societies, and universities. Dr. Menendez also holds a dual degree in civil engineering and architectural engineering from the University of Miami, from where she graduated summa cum laude in 2002. Her research interests include traffic flow theory, operations and control, traffic modeling and microsimulation, and sustainable transportation. She's the author of over 25 peer-reviewed journal papers, 1 monograph, and over 50 articles in conference proceedings. Actually, my research greatly benefited from her work, especially in my graduate school stage, and I still have her dissertation kept in my computer. So yeah, so today we're very happy to have her present her work on system dynamics of urban traffic based on its parking and related states. So without further ado, welcome Dr. Menendez.
Thank you very much. First, let me start by thanking everyone who's attending. I know it's early for some, late for another ones. Thanks to the Traffic Flow Theory Committee, especially to Jack Haddad and Jorge Laval. And big thanks to you, Shaw, for organizing the whole thing and setting it up and being patient with me. So today I'm going to be, the title of the presentation is System Dynamics of Urban Traffic based on its parking-related states. And as this is part of the ISDD presentations, evidently this was presented there, but with a slightly different name. This is the name that made it to the DRPB publication. The name in ISDD changed. So anyway, the idea, let me see if this works. It's not working now. The idea is that within an urban setting, we normally have parking systems and traffic systems, right? And we are all very aware that they really interact with each other. So the parking system, for example, affects traffic and traffic performance, potentially creating congestion, etc. One of the most common statistics, and I'm sure many of you are aware of it, is that one from CHUP that says that on average, 30% of traffic within downtown areas at rush hour, it's just looking for parking. So on the other side of the equation, we have how the traffic system affects the parking system. And this is not so trivial, but basically traffic performance can affect our ability to find parking. Think about the extreme case where the speed in the system is 0, then if you cannot move, you won't be able to make it to the parking place. So now the goal of this research was to model these interactions so we can estimate the influence of parking on traffic and vice versa. Once we do that, then we can also understand the effects that different parking policies might have on traffic performance or different traffic policies might have on parking. And if we understand that, then we can, in theory, improve the system. Now, traditionally, people have been looking at some of these interactions, but mostly through microscopic models to be a specific agent base. So you need to track specific vehicles and specific parking spots, and then you see how the vehicles match to the different parking spots, and with that you understand what's happening to the system. Now, we didn't want to do that because that requires a lot of information. So that's why we went with a macroscopic parking model. And that means that our data requirements go down a lot, but also our computational cost. Now, there's some works on economics that do use a macroscopic parking model, but they assume normally constant traffic conditions, for example, speed. So they would assume that speed is the same for the 2 hours or the 3 hours that I'm modeling this. Now, as we know, that's not very realistic because traffic conditions can change rather rapidly. So to avoid that kind of issues or to address these issues, we use a dynamic system where we're looking at time varying conditions of both the parking and the traffic side. Now, we do that through what we call parking state transition matrix. And this means that within this matrix, a vehicle can be in one of 3 possible traffic states or parking related states. Two of these states are within the traffic system and one is within the parking system. But all of them are parking related. So a vehicle can be simply non-searching, meaning driving, but he's not searching for parking, he's just going through the area, or searching for parking. So that means that you're driving, but you're trying to find a parking space. You have made a decision to park, you're just looking for the spot to do it. These 2 states are contained within the traffic system. In the third case, you can simply park. Once you find the parking, you're parked, and that's a third state and it's within the parking system. Now, the interesting thing is to understand how the number of vehicles within each of these states is changing over time. For that, we develop, or we call what we model what we call the transition events, and then we have 5 transition events. So we enter the area, we start to search, we access parking, meaning we actually park, we depart parking, and then we leave the area. Now, notice here that the arrow for leaving the area can come from 2 different populations. So you can actually leave the area after you have parked, or for the case of through traffic, you leave the area after you have driven in the area long enough, or whatever distance you require, right? So now, each of these transition events is modeled for very, very small time slices, say 1 minute. And within these time slices, we assume that we have steady conditions. So the system updates from one slice to the next. But within a time slice, we assume steady conditions, although because they're small enough, that's not so unreasonable. So then we end up with a single matrix that allows us to model the 2 systems simultaneously. So this matrix, remember, gives us the number of vehicles in each parking related state, right? From that, in the parking system, then we can get the number of parked vehicles and the parking occupancy, which we feed back to the matrix. In the case of the traffic system, that allows to calculate then the number of vehicles that are driving, either because of searching or non-searching. With that, we can get the traffic density and then the traffic speed, which we feed back to the matrix. With both the parking occupancy and the speed, we model the transition events that update the number of vehicles within each parking state, and then this starts again. Now, a very or relatively easy way to visualize this kind of matrix is with a queuing diagram, and I'm thinking most of you are very familiar with it. But on the x-axis we have time, and on the y-axis you have the cumulative number of vehicles that have gone through each transition event. So basically, you have the cumulative, you can plot the cumulative number of vehicles as a function of time that have entered the area, that have started searching for parking, access parking, that have departed parking, and that have left the area. And you do that by updating these lines through these thin time slices, right? Now, with this queuing system, we really don't need to track each vehicle. We don't need to know when someone specifically entered the area or access parking and how long that specific person stayed in parking. But we still can find the total search time or the total travel time, etc. So basically aggregated values from this. We cannot get this individual travel time because we know systems like these are not first in, first out. But the macroscopic indicators we do get. And normally for traffic control or parking policies, etc., all we care is about these macroscopic indicators. We don't care about the individuals, right? And what I'm going to do for the next few slides is show how do we model these transition events. This is the core part of the paper or the research. How do we model, or what are the formulations behind each of these transition events so we can update the matrix over time? So first, for entering the area, this is simply a model input. So we need to know the demand. We need to know how many people are going to enter the area. And out of those, how many people are trying to park at some point, and how many is just through traffic? So what proportion of the demand is simply through traffic? Then for starting to search, we assume that vehicles start to search after they drive for a given distance. We call it L, from non-searching to searching. Now, this distance, I will talk more about it later, but it can be fixed or it can come out of a distribution. It doesn't matter. Basically, we assume that people don't start searching right away. They need to enter the area, and once they're close to our destination, they start to search. Now, within this equation, we have two terms. This first term here is just the proportion of traffic that is actually looking for parking. From all the demand that have entered the area in the previous time slices, what proportion will try to park at some point, right? Beta is the percentage of the demand that is through traffic. We don't need to go into the details of the terminology. And then we have this gamma, which is a binary variable that indicates whether these people can start to search now or not. Now, for gamma to be positive or to be 1, two conditions must be satisfied, these two conditions here. One means these people have driven long enough, so longer than this distance. And the second condition is that they haven't started searching for parking before, right? So they haven't gone through this transition event before, because we assume people go through a transition event only once. Okay. Now, access for parking or access parking is the most complex piece of formulation here, so I will discuss it in a few slides. And depart parking. We assume that vehicles depart parking after they have parked for a period of time t, right? Now, this part of the formulation of the equation represents the number of vehicles, the total number of vehicles, or the cumulative number of vehicles that have access parking or that have parked in the last time slices, from the beginning until the previous time slice. So this is the total number of people that have access parking. And this is the probability that these people depart within this time slice, given the probability of parking lasting so much, lasting from the time they enter parking until now. So this is F of TD is the distribution of parking durations. And this is an input to a model. We need to understand, or we need to know beforehand, the distribution of parking durations. I don't need to know exactly how long each vehicle parks, but I need to understand the distribution, or to know the distribution behind the average parking duration. Then for vehicles leaving the area, remember, you could leave the area after you have parked, or in the case you're through traffic, you simply leave the area, right? So now, here we also have two distances. For the vehicles that have parked, we assume they can leave the area after they have driven this distance. And for the through traffic, we assume they can leave the area after driving this distance. So then here we have two terms. This is through traffic, and this is the vehicles that have parked. And as before, we have two gammas, now one per term. And these are binary variables that indicate whether these vehicles can actually depart in this time slice or exit the area in this time slice or not. For gammas to be 1, it follows exactly the same rationale as before. Two conditions must be satisfied. First, they must have driven long enough, meaning longer than this or this, depending on their case. And they haven't left the system yet, because again, you only experience each transition event once, right? Okay. So I said access parking was the most difficult one, and now we're coming back to it. So the formulation for accessing parking, or to understand how many people access parking, is based on probability theory. Now, first, we assume the network is relatively small, compact, and homogeneous, and that the parking spots are all identical and uniformly distributed. So that means that a driver has no specific preferences for one or another parking spot, right? So again, because the network is rather small and homogeneous, and all parking spaces are the same, for me as a driver, it doesn't matter to park here or on the next. So as soon as I see an empty parking space, if I'm searching for parking, I will take it, right? Now, we model this then as a ring, because an easy way to model homogeneous networks is just as a ring, where we have parking spaces and drivers searching around. So now at the beginning of each time slice, the locations of available parking spaces, in this case, these little triangles, are random. And we do that in order to account for the stochasticity of parking availability. You know, at some point a parking spot becomes available here, then another one becomes available here, or some other area. They're not necessarily uniformly distributed every time. On average, you might expect them to be, but in every time, not necessarily. Then the locations of the parking searchers are uniformly distributed. Why? To guarantee that the demand is homogeneously generated. And this was one of the basic assumptions, that the network is so small that it's used in a homogeneous manner. So then the locations of both the available parking spots, the triangles, or the driving vehicles are reset in every time slice. We do that so we can obtain the average number of vehicles that find parking without really being influenced by the specific location of this parking spot here within this time slice, right? Okay, so then with that we can formulate all the solutions, and they can be basically grouped into 3 cases. Now the differences between these 3 cases are given by the amount of distance that a car can cover within a time slice. So for case number 1, the distance is between 0 and the spacing between 2 cars. So if you look at the figure here, it will mean that this car in the top can drive any distance between 0 and this distance, right? So if you think about it, that means that for most cases, the whole network is not going to be covered. So there are going to be portions of the network that are not visited by anyone. It also means that a parking space can be visited at most by one searcher, because no trajectories overlap, right? So now, this term here, 1 minus d over L, is the probability that any given parking spot, one parking spot or one point, is not in this red area, it's here, right? Now, if I raise this to the number of parking spots, A is the number of available parking spots. So this whole term here is the probability that no parking spots are on this area, meaning that all parking spots fall outside this red area on this empty area. So evidently 1 minus that is the probability that at least one parking spot falls in this area. And if a parking spot, an available parking spot falls in this area, this driver can take it because there's no competition. No other driver will pass by that parking spot. So if we multiply that probability by the number of drivers that are searching for parking, then we will get the number of drivers that can actually access parking in this scenario, right? Okay, then I go to case 3 because it's the easiest one. And I'll leave case 2 for the end. So case 3 means that the distance covered by a single driver is longer than the network length. L is the network length. So this guy is going to do, potentially, is going to do this and come back. Now, not everyone is going to do it, because if you find a parking space before that, there's no need for you to continue traveling. But in theory, a parking space can be potentially visited by all searchers. It might not happen because people will park before, but it could potentially be visited by all searchers. And that means that either all searchers are going to find parking, in which case the number of people that access parking is just the total number of searchers, or if there's no parking spaces for everyone, if there's not enough parking spaces for everyone, meaning if the number of available parkings is smaller than the number of searchers, all parking spaces are going to be taken, and it's this part of the equation, right? So then the number of people that access parking is just equal to the number of parking spaces available at that point. Okay, case 2 is when the distance that a vehicle can drive is larger than the space in between two vehicles, but smaller than the whole network, right? So a parking space can be potentially visited by more than one searcher, but definitely not all searchers. Now, this is rather complicated, and you need to trust me because you have these P1 and P2, which are very, very complicated probabilities with a lot of summation stuff. But you need to trust me that this thing here, it's a probability, this term, it's a probability that a parking space, one specific parking space, is not taken by any searching vehicle, meaning it's not reached by any searching vehicle. Hence, this 1 minus that is the probability that a parking space is visited by at least one searching vehicle, right? If I multiply that by the number of available parking spaces, then I can find the number of parking spaces that get taken, which is the same as the number of people that can actually find parking during that time slice. Okay, so with that, then I can model the likelihood of finding parking. So I can say, well, the probability of finding parking, which evidently goes from 0 to 100, changes in this way, according to whatever way, according to the number of available parking spaces. So I can model the probability of finding parking as a function of the number of available parking spaces. Now, the number of available parking spaces can go from 0 to the total parking supply. It cannot be larger than that, so evidently. And then here we have the 3 cases that we saw based on the driving distance that a vehicle can cover during a single time slice, right? Now, you see that the lines have 2 colors here. And that's because in this specific case, for illustration purposes, we arbitrarily chose NS. This is the number of searchers to be here. Now, for all these values, it means that the number of available parking spaces, right, for all these values, it's smaller than the number of searchers. So that basically means that there's not enough parking for everyone. For all the values on the right side of NS, means that the number of available parking spaces here is larger than the number of searchers. So there is enough parking for everyone. However, that doesn't mean that everyone finds parking. So in the extreme case, so that's why you see these lower probabilities. In the extreme case, when the speed in the system is 0, so the average distance that you can cover is 0, you won't find any parking because you won't ever be able to make it to a parking spot, even if there is enough parking for everyone, right? So basically, the probability of finding parking is mostly affected by the number of available spaces and the distance driven in the time slice. Now, the number of available spaces is given here in the x-axis, and the distance driven is represented by the 3 cases, right? So in the first case, remember this is the case where the distance that you drive is smaller than the spacing between two vehicles. The probability, it's represented by this line over here. Now, this line can move within this whole range, depending on D. So if D is equal to 0, this line becomes a horizontal line here with a probability equal to 0, the probability of finding parking. When D is equal to the spacing between two cars, so every car covers a space into the car in front of him, the probability is given by this line over here, right? Okay. The second case, as you probably remember, is a little bit more complicated with two subcases and everything, but basically it moves within this range. So all the probabilities are within this range, depending on D. And for the third case has no range. It's very simple. So if there's not enough parking spaces for everyone, all parking spaces get taken. And the slope of this line is just the number of available parking spaces divided by the number of searchers, right? If there are enough parking spaces, then the probability of finding one parking space is 100%. Because there's enough parking for everyone, so all searchers find parking, right? Okay, so that was the core part of the model. But I started this presentation discussing how macroscopic in this case was better than microscopic because we didn't have to track individual vehicles, etc. However, if you look at the formulations, they do include a number of inputs. So one of the things that we wanted to do was check how feasible is for us to get all those inputs, and is it actually needed for us to get very accurate values for all those inputs. And these are the most relevant inputs that we have. The first two, these are the demand-related inputs, so it's the portion of the demand or the actual demand that it will end up trying to find parking, and the through traffic. Then some network-related inputs. We have the network length and the total number of parking in the network, A or this. Then I said we needed to know we needed information on the distribution of parking durations. We assume a gamma distribution because previous studies have shown that gamma is a very good distribution to describe parking durations. So gamma then has two parameters. It has a shape parameter and the average value. These are the three distances that I discussed before. These are the distances that we use to model transition events and the speed of the network, the free flow speed of the network. So basically what we did was a sensitivity analysis. And I'm sure you all know, but a sensitivity tells you how changes in the input affect changes in the output. So we use a global screening sensitivity analysis method to identify the most influential and the least influential parameters. Now we consider a parameter as highly influential if when you change their value slightly, you get big changes in the output. So small changes in the input give you big changes in the output. So now, I won't go into the details of the sensitivity analysis we use, but it is global, which means that it defines an influential parameter not only on its influence alone, but on the interactions with other parameters, etc. And we run over 100,000 samples to cover the whole input space for all the sets of parameters according to these distributions and these ranges. These are what we thought reasonable ranges for all the parameters. And what we got is that if we're trying to estimate the average cruising time, the most influential parameters are, not surprisingly, the traffic demand that will end up parking, meaning the people that comes to the area that wants to park, this one, the total number of parking spots that are in that area, not the ones that are available, but the total number of parking that is in the area, and the average parking duration. Remember, we were using gamma, and there's another parameter, the shape parameter. That one was not important, just the average duration. Now, if we are interested in getting the average cruising distance, the influential parameters are the same three plus the speed, the free flow speed. And that kind of makes sense, right? Because the average cruising distance depends on how fast you can go within the network. We also found that the network length is slightly important. So it does have some influence. But the rest of the parameters are non-influential. Now, this doesn't mean that you can have a model without those parameters. This just means that you don't need to have exact values for the inputs of these parameters. You can just have educated guesses and the answer won't change that much. You do need relatively good data on these parameters that I mentioned here, the demand, the number of parking spaces in the area, which you should have, and the average parking duration. And for the case of average cruising time, also free flow speed, plus the network length. Now, these are not so hard to get. But so this is very good news because specifically these distances that I mentioned before, we don't need to know them exactly. They're really hard to get. But we don't care. We can just have educated guesses and they won't change our output so much. So now what I'm going to do now is kind of illustrate the use of a methodology with two different case studies. One of these is presented in the TR/B paper, the other one is not because we just finished it. So the first one is a numerical example based on an abstract case, and the second one is a real example. So for the numerical example, we have a network that is 1 kilometer long, and there's no through traffic, so everyone that goes there is because they want to park. 21 parking spaces, and the average parking duration is 10 minutes. Some people want to park 5 minutes, some people 20, but the average is 10. So here we have the queuing diagram with the five transition events. And this is the demand, the blue one. This is people entering the area. This is a given. And as you can see, the demand is non-uniform. So you have a peak for some period, and then it goes down to 0. This is the cumulative number. So we're talking here about the slope of this, right? So then we were able to get the number of driving vehicles, total vehicles on searching. And evidently this one goes up, especially here, quite high. But this is a function of the demand because suddenly we have a high demand entering the system. So it just makes sense. Now what we can also see is that the travel speed goes down rather a lot for this area. When I have a lot of vehicles driving in the system, this makes the system very congested. And for some period of time, the travel speed becomes almost 0. So now, this is a very extreme case, but we were looking for an extreme case that allows to test the model. In the second case study, we'll see a less extreme case. Now, we can also estimate the proportion of searching traffic, so the proportion of traffic that is searching for parking. And we can see that it remains rather high while the parking is saturated. So here we have parking occupancy. And you see that this is high while the parking occupancy is around 100%. What does it mean to have a 100% or something close to 100% parking occupancy? It doesn't mean that vehicles are staying there, in our case, for the whole period. But as soon as one vehicle leaves, another one takes the parking spot. And this happens because in our specific case, we have for so many vehicles, and then the network is so small that there's a high density of searching vehicles. So as soon as one parking spot becomes empty, it can be easily replaced, right? Now, in normal networks, you might not have 100% in real networks. You will have something close to 100, but not necessarily 100, because there's some time between a parking getting empty and someone finding it. Now, what is interesting is the total distance traveled within each time slice, this graph, because then we have two peaks. With this big valley at the time conditions were the worst. Now, if you think about it, it actually makes sense because this valley here, or this drop in the distance traveled per time slice, actually corresponds to this time period where I had a lot of traffic searching for parking, but the speed was so low that people were not really moving. So the travel distance was was quite low. Now the problematic situations are when the speeds are not so low. So when I'm in this area and in this area, the speeds are relatively high, but the occupancy is still quite high, close to 100%. So then you have these two peaks of people driving a lot, just waiting for parking. So now, if you think about the mechanism for cruising for parking, it can actually work one of two different ways. Option number one is you have parking. Then cruising for parking is you're just trying to make it to the parking. You're trying to find the parking. That's not the situation here for these two peaks. Our situation here is option number two. It's like there's no parking. So all I'm doing is waiting for parking to become available so I can take it. So now, in real life, some people might actually stop and wait for parking next to the street, to a street with on-street parking, just waiting for a parking to become available. But it also happens that many people continue driving. And all you're doing is just wasting time until a parking becomes available, and then you can take it. So this is these two peaks represent very, very inefficient searching, a very inefficient searching state, because you're not really searching. You're just going around and wasting your time until another parking becomes available, right? So this means that policy results are not very straightforward. So here we compare the original situation with different policies. So just as a reminder, in the original situation, we had 21 parkings, and there was no time control. So you can stay there as long as you wanted. The average parking duration was 10, but some people parked less and some people parked longer than that. Then we tried to implement two types of policy. Policy A said, well, because our system is so congested and it's so bad, let's just increase the supply. So rather than having 21, let's test one option that is offering 22 parking spaces and another one that offers 23 parking spaces. Then policy B is, well, rather than changing parking availability, let's implement time controls. So I would tell people you can park here a maximum of so much. So option B1, the maximum time that you can park is 20 minutes. Now, remember, here we had a distribution with the average 10. So this means that some people are still going to be affected because some people would like to park more than 20, but a small population. Now, option number two, B2, we say the maximum amount of time that you can park is 10 minutes. That means that a bunch of people are going to get affected, right? Now, in a real situation, people might say, okay, I need to move my car and then we'll start looking for another parking space. Here we assume that people would actually depart parking and just leave, right? They cannot look for another parking space, or they decide not to look for another parking space. So if we look at the effects of the time control, this is great. You reduce the travel time or the searching time, and you reduce the searching distance. That's perfect. But if we look at the effects of adding supply, we add just a little bit more. We don't add enough supply to get rid of the congestion. So we add a little bit more. And this reduces time, but it actually increases the travel distance. That's because we managed to increase the speed a little bit, but actually the ability of a vehicle to find parking remains rather low. So outside the congestion period, the travel time is slightly reduced, but during the congestion period, it stays more or less the same. And because now I have a slightly higher speed, the distance is higher. Remember, during the congestion period, people are just driving, waiting until a parking spot becomes available. So if I do this at a higher speed, I would just drive longer, not necessarily wait less, right? Okay, so this is important because it highlights the fact that we really need to study policies from different angles to understand the full effects that they might have on the traffic conditions, especially parking policies. So some policies can actually reduce time, but at the same time, but simultaneously increase the travel distance, and that's not good because we all know the negative effects or the negative externalities of longer travel distance, emissions, space consumption, etc. Okay, so now the second example, it's based on the city of Zurich in a small area within the city. We call it Jelmoli area. It's this area because there's a parking garage called Jelmoli. and a store with that name. So the area has a radius of 300 meters, and it contains 539 public parking spaces. This means the parking space that anyone can use, right? There's also a number of private parking spaces, but we don't take them into account because this will mean people that don't cruise for parking. So this will be the parking that you get in at your home, your private, or at your office. So you would simply go there, but you don't need to look for parking. So now these parking spaces are distributed between 2 garages, 332 are in 2 garages, and 207 are on-street parking. Normally you wouldn't put parking garages and on-street parking spaces together. But in this case, first, the area is rather small. Second, parking in Zurich is quite problematic. So people are just happy to find parking, I guess, in whether it's a parking garage or on street. So people are not so sensitive to that. Plus also for simplification purposes, to be honest. Now the area has 106 links, and that's equivalent to 7.7 kilometers if I calculate all this yellow stuff. So we had 2 sets of inputs. One was the cumulative number of people entering and leaving the area, and the other one was the histogram of parking durations. Within this, we knew how many people were through traffic and how many people were going through parking. Now, the 2 sets of data come from a demand model developed by another group at this university, and this demand model has been fed with real data. So this is, in theory, based on real data from the city of Zurich for an average working day. So this is an average working day. Now, the purpose of this case study for us was actually to validate or understand whether a model made any sense in reality. So for that, we needed to create some outputs that we could compare with reality. And the only output that we could actually get also from real data was the number of available parking spaces. So this is what we use to validate the model. So this is the data that we got through our model. So we see that the number of parking spaces actually increases early in the morning and then decreases. It becomes almost 0 between 11 and 3 p.m. and then it starts increasing again. And then you can see that there are some cars that park overnight. So these are the people that depart here early in the morning. Is people, I don't know, people, this is the center of Zurich. So it will be people departing at 1 a.m. or 2 a.m., etc. Now, remember, this is data from an average day. This is real-time, real data that we collect in real time from a website in Zurich that provides real-time data on parking availability. Now, this is for a random day. We collected this. You cannot collect historically. You have to collect it in real time from the website, and you don't even get the actual numbers. You get the graph, and then you have to. But anyway, we collected several days, and all of them look more or less the same. One is higher here, lower here, but basically means that parking in Zurich is rather stable, so there are no surprises. Everything works the same more or less every working day. And so this is just one random day, working day. And as you can see, it fits pretty well our distribution, or what we had observed, which is a very good indication that despite the simplicity of the model, we're able to capture the main the main factors affecting parking availability over time, at least within this small area of the city of Zurich. Then we could also see the number of searches over time. Basically, it's rather low, and it increases it's rather low for the whole day, and it becomes quite high between 10 or 11 to 4 p.m. This is the time when everyone goes for retail purposes, or shopping, or tourism, etc. And we were able to plot the searching time based on the arrival time of vehicles. Now, this kind of assumes FIFO. We normally don't need to assume FIFO, but this specific graph does assume, because we're not looking at it from the system perspective, but more from the user perspective. This is very important for users because you would say, well, if I go to a city between midnight and 10 a.m., I will normally spend between 0 and 1 minute searching for parking. However, if I go after 10 a.m., my searching for parking time will increase. And if I go there at 12, I may spend a total of 13 minutes looking for parking. So this kind of gives you an idea of more or less what would you expect as you're searching for parking time, depending on your arrival time to the system. And then we can get anything else that is related to the 5 transition events that we measure. Remember, our input was entering the area and leaving the area. So we had 2 lines, and we added the other 3 lines, the starting to search, the accessing parking, and the departing parking, based on the model itself. And here you don't see them well because they overlap with each other, but we can get any information that comes out of this queuing diagram. So what are our contributions? Well, basically, we propose a new parking state-based matrix to model macroscopically a dynamic parking system. Now, there are 2 keywords here, microscopic and dynamic. The fact that it's macroscopic means that we only focus on average values and probability distributions. We didn't have to track individual vehicles or individual parking spots. And this saves a lot on data collection efforts, but also reduces the computational cost quite a bit, right? Now, the second keyword was dynamics. We look into the dynamic conditions by taking into account the time-varying performance of the traffic, for example, how density and speed change over time, and the parking, so occupancy or parking availability over time. And this allows us to better emulate reality. So now we have a very limited number of inputs, those related to the travel demand and supply, like how many people are coming and how many people would try to park in this area or how much is through traffic. General information on the traffic network, like the total length, these are things that you can easily measure. And then properties like saturation flow or free flow speed. And the distances that I mentioned before for the transition events. But if you remember, for these distances, we don't need very exact values. We can live with educated guesses, right? And then we can get a bunch of microscopic outputs. Those related to searching conditions, so how long you search, what proportion of traffic is searching, traffic conditions, how many vehicles you have, and what is the speed on the system, etc. Parking conditions, how much parking availability you have, or occupancy, either way. And then environmental indicators such as travel distance. Now, how do we use that? Well, one example is what I show to evaluate and design different parking policies, because we can completely understand, or we can better understand their effects onto a traffic system, and this, in theory, we could optimize then these policies, right? We could also use them for traffic operations and control. Because the model is macroscopic, it allows us to do fast computations, and this is very useful for short-term prediction. So we could actually use this model for short-term prediction of traffic or parking, and then implement management strategies in either of the two, right? And the last thing, this is some work that we have going on right now. We can use this model to evaluate when and how to use different parking guidance systems. So when and where to provide information to the users about parking. When does it make sense? When does the return to investment ratio is actually positive? Yet, evidently, this is a model and it has some limitations. So this we address here. We're trying to address some of these limitations. Other ones we're just mentioning. Although I think we're actually working on all of them. We're looking at, so far, we look only at homogeneous networks, and this is a kind of a big limitation because we can only look at small areas. If we want to look at big areas, then we need to start considering heterogeneous networks where people are not completely indifferent between parking spaces, right? So far, we haven't made a distinction between on-street and off-street parking choice. But especially as we start looking into bigger networks, this is going to become quite important. We have also assumed that the demand is constant, and that's not very realistic because for the extreme scenarios where you have long cruising times or searching times, the demand will change. Like some people might just give up the search and go back home or go to another destination. And the last thing is we can use this to better understand pricing schemes and our reservation systems, especially if we consider on-street parking and off-street parking. And with that, I finished, and I forgot, I had this in mind, I completely forgot to say it at the beginning. I need to give credit to Jin Xiao, my co-author, the first author here, this one. She has done most of this work. She is a PhD under my group, and she will actually be presenting or doing the final presentation for his PhD in less than a month. And this is part of her PhD dissertation. So majority of the credit goes to her. Thanks to her, and thank you all for listening. And now if you have questions, I'm happy to discuss.
Thank you, Monica. It's a very nice presentation, very good work, and also congratulations to your talented student, and good luck to her final dissertation defense.
Yeah.
So that's great. So to the audience, if you have any questions, please feel free to raise them. I think the best way is to unmute yourself and speak out, or if you want to take some time to organize your words, you can use a chat box as well. So you see actually on the control panel there is a sub panel called chat, and you might want to type your questions there as well. So when you send out your message, please make sure that you send it to organizers and panelists only. Again, organizers and panelists only, and this way everybody will see it. Okay, so any questions?
Okay, that's either very good news or very bad news.
Is there someone speaking? All right. Okay. Maybe while others are thinking about it, I can just ask a question, and then you guys can get better ones in. So Monica, yeah, it's a great work, and I really appreciate the analytical perspective of this work and utilizing the homogeneous setting, macroscopic fundamental digraph analysis, maybe. So I wonder, and in recent years, parking systems become growing a lot, and then users may get advanced information and book the parking lots ahead of time, so that they don't need to circulate. They can directly go to the spot they reserve.
Sure.
And so is there a way to integrate such advanced information in your analytical framework?
So there are two things that could happen. One is just you provide information alone. So where you say there's free parking there, just go there. You don't have the chance to reserve. That's one thing. Another one is you also include a reservation system on it. So on the first topic, we're about to submit another paper on this where we have been looking whether it makes sense or not and when it makes sense to have it. And I think as a user, I would always like to have information on parking availability. Honestly,
Sure.
If I'm driving, I want to see where parking is available. But from the operator's perspective, it doesn't always make sense because I don't know if wait, let me see. In the case where you have these two pics, in this case where people were driving just not because they couldn't find the parking, just because there was no parking. So it wasn't lack of information. So in cases like these, information won't really help you to get to the parking because you're simply driving, waiting for a parking to appear. So information is rather useful when the number of searchers is more or less similar to the number of available parking spots. And this happens just on a specific periods of time. Now on the second, and so for all this analysis, we have used this model. Now the second topic was, can I use reservations? And evidently reservations would take care of cruising time completely, will eliminate cruising time. So you can also have a portion of vehicles that do reservations and a portion that doesn't do reservation. Yes, you can integrate that easily into a model.
Great, thank you. Yeah, okay. That'll be, I'll look forward to looking at your other paper on parking information. And you got another question from Yao Chen. Looks like
how can the on-street parking and off-street parking be different in terms of users' preference? How can the users be categorized in the feature study? So I have another PhD student who's actually working on putting separating on-street parking from off-street parking in terms of preferences without still going into the microscopic level of each individual user. In general, parking garages, you can assume that have a different pricing structure than on-street parking. In the case of Zurich, we didn't assume so, but in general, it's not unreasonable to assume that. And if then they have different pricing structures and you implement pricing within this system, then you can create different, people will have different preferences for them. How can they, then the second question is, how can the users be categorized in the feature study? So, because we still don't want to track individual users, what we're trying is to track, we have distributions for the value of time of users. So again, because we don't want to be, become microscopic, we need to keep everything at the probabilistic level. And so we would need to have a distribution of value of times for users, and based on that, we have a probability of acceptance of either an on-street parking or a garage parking, depending on the prices. We haven't finished that, but that's the idea that this other PhD is pursuing right now. Does that answer your question, yeah? Okay, I hope it does. Ah, okay.
yes, yes, thank you. This person
Thank
said.
you. Any other questions? In Zurich, the on-street parking. Oh, this is for Yao. Okay, so Jean Chao is the PhD student involved on this, and I don't know if she's asking a question. In Zurich, the on-street parking is also made often for short duration parkers. Yeah. So this is true for many locations. I think Jean is bringing up an important point. Time controls are more often implemented in on-street parking than off-street parking. So even if you don't implement pricing, that could also be another strategy or difference between to differentiate on-street versus off-street parking versus garage parking, the time duration. Any other questions or?
Any other questions? Okay, if not, then again we thank Monica for the very nice presentation and a great work, and we also thank Jean Chao for the assistance and the great work to make this work out to us. And I think finally thank all of you for the attendance. I really appreciate that. And next seminar will be around this time next Friday, and stay tuned, and I'll send you the announcement very soon. Again, thank you so much for all of this, and the meeting adjourns. If you have questions, please feel free to contact me.